In this video, we're going to talk about how we use exponential functions to represent percentage growth and decay. And the way we do that is by considering the value b. To make b grow, or to have b be a growth factor, we want it to be a number greater than 1. So what we're going to do is take our percentage rate of growth, write it as a decimal, and add it to 1. That's how we're going to construct our b. It's important to note that if r is negative, or if we have some percentage decrease, we're going to think of r as being a negative decimal, and so that's going to result in a number less than 1, causing our decay. So let's look at how we're going to use this idea to create functions. So here we have a population in 2000, in the year 2000 is 1,700, and the population is growing by 3.77%. So our initial value, A, is still going to be the starting value of the population. Remember, here T is years since 2000. So starting in the year 2000, we have a population of 1,700. To construct the B value, we're going to take 1, and since the population is growing by 3.77%, let's think about R. If R is 3.77%, we want to turn that into a decimal by moving that decimal place 2 places to the left. So I'm going to move that 2 places to the left, and the result will be that R is 0.0377. So to get our growth factor B, we're going to take 1 and we're going to add to it 0.0377. So the population P will equal our initial value, 1,700, times our value of B is 1 plus 0.0377 to the T. So P equals 1,700 times 1.0377 to the power of T. This function has an initial value of 1,700 and a growth rate of 3.77%. We add that 0.0377 to 1 to make the new growth factor B. So let's find the population in 2000. So note again up here that T is years since 2000. So if I want to know the population in 2000, that's 7 years since 2000, so we're going to plug in 7. P of 7 equals 1,700 times 1.0377, and T is 7, so this is to the 7th power. It's important to note here, and I'll do an example below using the graphing calculator, that we need to do the 1.0377 to the 7th power first. So if you're using a calculator other than our graphing calculator, make sure you're following proper order of operations. If you're using a TI, you can basically put this thing in exactly, and the result will be 2,202.681. Since we're talking about the population to the nearest person, that's 2,203 people. If we want to find the population in 1998, that's 2 years before 2000. So here we're actually going to plug in -2. We're going to plug in -2 for T. And if we enter that value into the graphing calculator, we'll get 1,578.721. And again, if we round that up to the nearest person, since it's 0.7, that would be 1,579 people. So that's how we model percentage growth. Let's now look at percentage decay or decrease. In this example, we have a starting value, an initial value of 2,200 cells. And the cells are going to decrease at a rate of 3.4%. So let's talk about that. Since it's decreasing, R is going to be negative 3.4%. If we write that as a decimal by moving that decimal 2 places to the left, that's negative 0.034 written as a decimal. Our initial value A is still our starting value, which is 2,200 cells. But now when we find B, it's 1 plus R. Well, that's 1 plus negative 0.034. That will give us 0.966. Notice how that is a number less than 1. That is what's going to cause the decrease, and specifically, in this case, a 3.4% decrease. So putting our function together, B will equal 2,200 times 0.966 to a power of t. So if we now want to know how many cells are left 5 hours into the experiment, B will equal 2,200 times 0.966 to the 5th power. And again, be careful with your order of operations here, making sure we do exponents first. The result here will be 1,850.582. And depending on how we want to round, we can either round to 3 decimal places, or rounding that to the nearest cell would be 1,851 cells. You'll notice that that number is less than the starting value of 2,200, which is what we would expect. The number of cells should be decreasing.